the semiconductor manufacturing and power industries, high-purity water is vital to a plant's productivity and profitability. And the purer the water, the better. Over the past few years, tremendous advances have been made in water purification technology. At the same time, tremendous advances in high-purity water monitoring have made it possible to take advantage of this technology. This water has been purified by reverse osmosis and ion exchange. The resistivity is 18.25 megaohms per centimeter, a level that corresponds to about 300 parts per trillion dissolved solids. So, is it pure or not? While resistivity can tell you that contamination is present, it can't tell you what contaminants are present. And even minute quantities of certain ions may be enough to ruin a batch of semiconductors or cause a power plant to shut down. Because ions are electrically charged, integrated circuits are extremely vulnerable to them. Some ions can migrate through silicon, causing a device to fail long after fabrication. Others cause unwanted corrosion that also result in device failure. When you consider that a semiconductor wafer may be exposed to thousands of gallons of water during fabrication, it's easy to see why water purity is critical to yields, performance, and reliability. A few years ago, 18.25 megaohm water was pure enough, but as geometries go below half a micron, even 300 parts per trillion, maybe 290 parts per trillion, too many. In nuclear and fossil fuel power plants, the situation is different, but many of the problems are the same. In these plants, steam produced from high-purity water is used to drive steam turbines that generate electricity. For maximum operating efficiency and lifetime, these turbines must be carefully maintained. According to the Electric Power Research Institute, more than half of a plant's maintenance costs are due to corrosion. Even subparts per billion levels of corrosive ions over time can lead to problems that can cost hundreds of millions of dollars. By tracking ions in the steam cycle, utilities can not only avoid these problems, they can cut maintenance costs, increase uptime, and improve profitability. The method of choice for high-purity water monitoring in both of these industries has been Dionex ion chromatography. Dionex systems can monitor ions below 10 parts per trillion, more than an order of magnitude lower than resistivity or cation conductivity meters. What's more, even at these levels, ion chromatography accurately identifies which ions are present. This information can then be used to pinpoint and eliminate sources of contamination. Recently, Dionex invited experts from the semiconductor and power industries to share their experiences and views on high-purity water monitoring. Here are some selected excerpts from the power industry presentations. Dionex has been involved in power plant water monitoring for over 20 years. Throughout that time, we've been fortunate enough to work with EPRI's Thomas Passel, who provides this insider's perspective on the past, present, and future of nuclear power plant water analysis. First, Tom shares with us some of the disasters that have happened that got ion chromatography integrally involved in power plant water analysis.
Disasters such as this, where you see the turbine is coated with white salt, and in this case, probably sodium sulfate or caustic. In any case, a beautiful example of how it goes, I should say in June of 1975, about a month after I came to EPRI, the Rancho Seco station experienced a crack in its turbine blades and in its turbine discs, and this is a particular picture of that keyway, and it was eventually traced to the condensate polishers not being properly managed. And here's a closer view of that crack. Well, these got the attention of the highest levels in the utility and said, we've got to do something about this, and it almost invariably went back to dealing with the water.
Whenever possible, it is advantageous to put monitoring and control instrumentation online.
By the way, one of my mottos is if it's worth doing online, because the things that are of interest to you that will help you solve the problem will be happening while you're asleep. Things will be going bump in the night. And here's the bump in the night that occurred at Rancho Seco in January 1982.
The ability of ion chromatography to identify individual contaminant ions is critical for identifying sources of contamination. Here, Tom shares an experience with ion chromatography for solving the problem that occurred at Rancho Seco.
Practically no sulfate was taken out, and sulfate turned out later in many other areas to be the culprit and the thing that caused ion chromatography to be allowed in the door.
Tom Passel has shown that ion chromatography has become a critical tool for identifying contaminant ions in power plant steam cycles. Fred Bianco is the chemistry supervisor at the Union Electric Nuclear Facility in Fulton, Missouri. Fred used a Dionex DX500 ion chromatography system to improve his ability to monitor trace sodium in his water purification system. Here is his perspective on the need for a better method for sodium.
We had a need a couple of years ago to figure out what was going on with our sodium contamination in our system. And basically, sodium is bad, as Tom alluded to. We've got $750 million at stake. Those 4 steam generators are pretty expensive little animals.
Conventional ion selective electrode techniques have difficulty measuring at low parts per trillion concentrations. Fred was able to reliably make measurements with ion chromatography as low as single-digit parts per trillion concentrations.
So I did do some spike sample recoveries on those low-level samples when feed water would run around 20 parts per trillion. I do some spike results, and we could get some pretty good repetitive results from the system. So I feel pretty confident, you know, when I'm telling my supervisor that feed water sodium is 8 parts per trillion, then it's 8 parts per trillion.
The mark of a good analytical technique is one that produces the same result in the hands of many different people. Here is his experience with Dionex ion chromatography.
Now the interesting thing is, in all of this test, I'm not doing any of this. I've got 16 different people, and on any one day I'll have somebody assigned to me, and I basically have to come up with a regime for the guy to do for the day, and he basically does whatever I need him to do, and I'm accumulating all this data. So whereas somebody might sit down and do all this himself, I feel like I've got a pretty broad database to draw from, and I feel pretty confident that the methods work fairly well because 16 people are using them.
This new capability allowed Fred to observe excursions he was never able to see before.
We were running around 120, 200 parts per trillion, and we had put a polisher in service, and we had this excursion right here. And this happened over a period of about 7 hours. Now, 2 years ago, we wouldn't have been able to do this. 2 years ago, that 1511 sled out there monitoring that vessel would have read 40 parts per trillion the whole time and wouldn't even hiccup. Okay? And that sled in the lab that monitors the steam generators would have went up a little bit, and everybody would have been running around going, what are we going to do? What are we going to do? You know, so this allowed us to make the right decision.
Ion chromatography provided Fred Bianco at Union Electric with better detection limits and reliability for sodium than previously possible. This allowed him to better understand and better control his high-purity water system. We heard real-world examples of how ion chromatography provided unique capabilities for measuring difficult-to-measure species, such as sulfate, at concentrations never before possible. The ability to identify individual species allowed the identification and elimination of sources of contamination. This, in turn, allowed the optimization of high-purity water systems, reducing operating costs, preventing unnecessary plant downtime, extending the lifetime of plant components, and preventing catastrophic component failures. Now, let's hear from the electronics industry. In the electronics industry, just as in the power industry, the ability to identify and track ionic contaminants in high-purity water down to parts per trillion concentrations is of central concern. Lynn Venata is an analytical chemist at Texas Instruments in Dallas, Texas. She offers some practical advice on measuring parts per trillion concentrations of anions and transition metals using laboratory ion chromatography. Lynn Venata chose the Dionex AS11 column with gradient elution because of the AS11's excellent resolution of organic ions from inorganic ions.
But this is 50 parts per trillion again, but I've only had to concentrate 50 mils, and I get this kind of chromatography.
Achieving accurate results and linear calibration curves at parts per trillion concentrations is not for the faint of heart. Lynn outlined some good laboratory practices for trace analysis. Here are her results using these techniques.
These were the actual concentrations that I ended up with, and I did 5 replicates. 5 is the maximum number of 50 mil samples that you can get out of one of those tissue culture flasks. But this was a mixed standard, and all my RSDs were less than 10%. And then I ran a calibration curve, doing 2 injections for each of these 4 levels, and again a mixed standard, and the correlation coefficients were 0.99 or better for these, and then 3 nines on the top 4. So I think this method can be precise and accurate.
Lynn also demonstrated that transition metals can also be accurately measured at parts per trillion levels.
This is a chromatogram for these 5 metals, and I have, it's a mixed standard with 100 parts per trillion, and again I'm concentrating 50 mils. And these were the actual concentrations in the mixed standard, and all of my RSDs were below 10 except for nickel.
Marjorie Ballas of Ballas Analytical Laboratory in Sunnyvale, California, shares with us what she considers to be the analytical needs for high-purity water in the future. Marjorie is a leading authority on ultrapure water in semiconductor manufacturing. We now have the technology available to produce pure water down to the low parts per trillion quality. Marge suggests that the key issue today may not be how clean we can produce water, but how clean we can keep the water once it gets there.
You ask yourself the question, well, how can that be? And one of the things that we're finding out now is that the water can be excellent, but the air immediately above the water can have significant amounts of anions in it that we can actually measure it. So it is no longer in semiconductor industry a matter of what kind of water did I deliver. It's a matter of how clean could I keep it when I got it there.
Marge boldly suggests that while specifications today are at PPT levels, tomorrow's advanced integrated circuits may need measurement down to PPQT, parts per quadrillion levels.
You can see we're working in the PPT level. That's not good enough for our industry. It won't be good enough for the 300 millimeter technology. They want PPQT level.
Marge shares her thoughts on the many challenges for the high purity water field in the future.
Just to give you a quick rundown on how much water we do use in the industry. Motorola in the Austin area used 1.1 billion gallons of water in 1993, and that was before their new plant was completely functional, which was Fab 11. Fab 11 is now completely functional, and they are already building 2 more fabs. Cost probably in 94 and 95 will get up to 60 million. This is one of the most significantly high cost aspects that we have in producing wafers today, is the cost of water. Water is the only commodity that goes up, and quantity of use the same as the size of the wafer goes up. So we have many future challenges: specification, standardization. How do you standardize each other's water standards? They made them from water. What did their water look like before they put standards in them? These are significant analytical questions we've never been confronted with before. Where is the equipment going to come from that we need to analyze water? And then the big question, how do we stop using it? So any of you who are in here, this is a good field to be in right now. There are many really significant challenges.
Dionex has played a key role in providing the analytical technology needed for the semiconductor industry. The ability to measure contaminant ions down to low parts per trillion concentrations and to identify which contaminant ions are present allow semiconductor manufacturers to optimize their high-purity water systems and to assure that the highest possible quality water is delivered at all times. Better quality water and chemicals means better yields and improved device reliability. Dionex has been an innovator in the field of trace ion analysis and continues to expand the frontiers of the field. Dionex's goal is to make methods and instrumentation simpler and more sensitive. Perhaps the most important new advance is the determination of trace ions in high-purity water by direct injection ion chromatography. With this capability, ion chromatography can reach low parts per trillion detection limits for anions and cations faster and more easily than methods that require sample preconcentration. Edward Kaiser and John Riviello, both chemists at Dionex, were responsible for the development of this capability. Here, they highlight some of the technology that made it possible. The first step in improving detection limits was to improve the system hardware.
To begin our discussion about hardware, I looked at three significant areas. That's the pump, the conductivity cell, and then temperature effects.
Improvements in the flow control algorithms of the pump, the design of the conductivity cell, and active temperature stabilization of the conductivity detector improved signal-to-noise by a factor of several-fold. The next step was to improve the chemistry. Ed has shown that since the eluent is suppressed completely to water, better detection limits can further be achieved by injecting larger volumes of sample.
This is 10 ppb of fluoride, and it was interesting to note how by changing the sample volume from 25 microliters up to 750 microliters, I was increasing my response, but not sacrificing any peak resolution.
Another major advancement in chemistry is the use of microbore columns for high-purity water analysis. Microbore columns are half the diameter and 1/4 the volume of standard bore columns. This means that for the same volume injected, microbore columns produce 4 times the signal. So by simply going to microbore columns, we improve detection limits by a factor of 4 for the same volume injected.
The way the geometry works, it's a 4-fold advantage. And the way that works is that for the same amount of sample, both in 2 millimeter and 4 millimeter, you can get a 4-fold signal improvement.
The third area of improvement in the DX500 system for high-purity water is in the area of software improvements. PeakNet includes a number of data smoothing algorithms that reduce baseline noise while preserving the analytical signal. These algorithms can further improve signal-to-noise several-fold. Here, Ed compares the same chromatogram before and after data smoothing with PeakNet.
We significantly cleaned up the signal. Peak areas didn't alter by more than 2%, and so I just look at this as another toolbox, another tool in the IC analysis toolbox for doing trace analysis.
These improvements in the hardware, chemistry, and software of the DX500 system have improved detection limits by a couple of orders of magnitude relative to older generations of ion chromatography instrumentation.
A look at how this all comes together here. I made a standard at kind of the high PPT to low ppb range, and have utilized that injection volume of 750 microliters and get very nice peak response. In this case, I made this power matrix here of 8 ppm morpholine and was able to see similar chromatography peaks coming off at similar retention times, and was able to quantitate without any loss of resolution. And as far as precision for one of these matrices, I went to 8 ppm ethanolamine with 300 ppb ammonium hydroxide, and with that reagent delivery module, made replicate injections and came up with precision RSD values less than 10%.
John Riviello, staff research chemist at Dionex, has demonstrated that the same improvements for anions using the DX500 can be achieved for the determination of cations.
The nice thing about this approach for the cations is first the inherent sensitivity of or detection limits of the cations is very good. Adding a larger loop makes it even better. There is no detrimental effect on the chromatography. Here are detection limits for the CS12A 2 millimeter system with a 25 microliter and 1,000 microliter loop, and you see detection limits at the low parts per trillion level, ranging from 7 to lithium to about 50 parts per trillion for calcium.
Here are some of John's thoughts on the benefits of the new approach for high-purity water analysis.
The advantages of this is that basically it's simpler to implement because you don't need a sample pump. Again, since you're using a fixed volume sample loop, the precision of that injection volume is very good. It is also simple to automate because it's basically running just like a normal fixed loop injection system would run, and certainly can be used online.
We've heard from industry experts how ion chromatography has become a critical tool in both the power industry and the semiconductor industry. We've also seen some of the dramatic new advances that have taken place in the technology for monitoring ions in high-purity water. These technology advancements are making possible some important economic benefits for both the power industry and the electronics industry. In the power industry, ion chromatography has improved power plant economics by helping to avoid catastrophic component failures, increasing power plant component lifetimes, and reducing unnecessary power plant downtime. In the semiconductor industry, ion chromatography has been used to increase yields and improve device reliability. And we've seen how Dionex is continuing to advance technology to match the increasing analytical challenges of the future. Of course, every semiconductor and power plant has a unique set of requirements, objectives, and operating procedures. And Dionex offers a range of ion chromatography systems, columns, and accessories to meet these needs. The DX500 is a versatile research-grade ion chromatography system capable of performing the complete range of high-purity water analysis applications. The DX120 is an economically priced system designed specifically for routine monitoring. The Series 8200 online analyzer continuously monitors up to 17 different sample streams without operator intervention. A complete line of columns and other accessories provide for highly selective and sensitive analysis of high-purity water, as well as other types of samples. And PeakNet, a Windows-based chromatography workstation, automates all data analysis, management, and documentation operations. In addition to these instruments, there's something else Dionex offers that is invaluable in any high-purity water monitoring program. That is the expertise that comes with 20 years of experience solving high-purity water analysis problems. You can take advantage of this expertise and find out more about the complete line of Dionex ion chromatography systems and technologies by calling your local Dionex representative.
In the U.S. and Canada, call 1-800-723-1161. Outside the U.S. and Canada, contact your local Dionex sales office.
Thank you for your interest in Dionex ion chromatography. We look forward to working with you soon.